Linear and angular kinematics. Linear speed in rigid body rotation. So when a rigid body rotates about a fixed axis, every particle in the body moves in a circular path. The circle lies in a plane perpendicular to the axis and its center is on the axis. The speed of a particle is directly proportional to the body's angular velocity. The faster the body rotates, the greater the speed of each particles. Now consider these three particles in the figure that rotates about the center of the circle. So at constant distance r from the axis of rotation, so it moves in a circle of radius r at any time the angle theta and the arc length s are related by s is equal to r theta. If you take the time derivative of this, we have this derivative of s with respect to time equal to r times derivative of theta with respect to time, which is equal to the linear velocity equal to the radius times the angular velocity. So this is the relationship between the linear and angular speed. As you can see in the figure, as a particle has higher radius, it has a greater linear speed. Comparing the three dots, the green dot has a greater linear speed compared to the red one, which is more closer to the circle, to the center of the circle. The linear acceleration in rigid body rotation. We can represent the acceleration of a particle moving in a circle in terms of its centripetal and tangential component. So the centripetal component of acceleration is associated with the change of direction of a particle's velocity. While tangential component of acceleration acts to change the magnitude of the particle's velocity and is equal to the rate of change of speed. Now let's consider this one. Let's say, let's consider at this point of the particle. Let's say this one at this point. This particle. Since it is moving, let's say it's slowing down or increases its speed, going faster. Either way, let's say it has an acceleration, angular acceleration. So angular acceleration of a circular motion, let's say, is this one. And it has a component which is called centripetal and tangential. We know that the centripetal acceleration is directed toward the center of the circle, while tangential, as defined as a tangential line, is cross the circumference of a circle once. So the tangential is perpendicular with the radius. Say this one. So this is our tangential, the green one, and the yellow one is our centripetal. So this made up the component of our acceleration. So aside from the given formulas for centripetal acceleration, tangential acceleration, we can also get this one using trigonometric function by setting the angle between any of its components. So again, so here's our acceleration, angular acceleration with the blue one, and it has component of free tangential, the green one, and the yellow one, which is centripetal acceleration. Now let's have an example problem. An athlete whirls a discus in a circle of radius 80 centimeter at a certain instant. The athlete is rotating at 10 radian per second, and the angular speed is increasing at 50 radian per second squared. At this instant, find the tangential and centripetal component of the acceleration of the discus and the magnitude of the acceleration. So we have here the pre-valley diagram. So we have here the discus, the orange one, and we have here the acceleration, angular acceleration, and the component is the centripetal, which is along the arm, which we will consider as a radius, since the arm of the athlete makes a circular motion, a circular path, and the radian is this one, perpendicular with the radius or the arm. Okay, so the pre-body diagram is here at the right side. So this okay. So when you look at the top view, okay po. So the path discussed is here, the circular one. The arm is the radius with 0.8 meter, and a tangential, which is also where this centripetal acceleration is along, and the tangential is here, perpendicular with the arm, and the angular acceleration is this one. So we're looking for just a tangential and centripetal component of the acceleration, and also the magnitude of the acceleration. Okay, so let's solve for tangential and centripetal acceleration. So for tangential, we have our formula, which is R alpha. So our radius is 80 centimeter. Converted into meter, we have 0.8 meter. And our alpha, or angular acceleration is 50 radian per second squared. Therefore, our tangential acceleration is 40 meter per second squared. Now, if you're going to ask why the unit radian is cancelled out. So remember the ratio S over R, where we can get the theta. So theta is equal to S over R. And the unit for S is in length, let's say in meter. While radius, the unit for radius is also in length, which is, let's say, meter. So if you're going to divide this meter over meter, we will cancel the unit for the length. And instead, we represent the angle with the unit radian. So radian is a symbol only, or to represent an angle, wherein this angle is actually unitless, considering this formula. So again, particularly theta in radian, or the angle, is unitless or equal to 1. So here in computing the tangential acceleration, the radian will be disregarded since it is equal to 1. So we have here ang tangential acceleration. Now, for the centripetal acceleration, our formula is angular speed squared times the radius, which give us 10 rad per second squared times 0.8 meter, which is equal to 80 meter per second squared. Now, to get the magnitude of the acceleration, it is equal to square root of the radian squared plus tangential acceleration squared, which is equal to square root of 40 squared plus 80 squared, which give us 89.4 meter per second squared. Okay, so let's have your sample problem. Check your understanding. So answer this one and write your answer in the comment section.